This is the 3 nails demonstration of corrosion in respect to cathodic protection. We can first examine what the meter is telling us. Switch it on to volts. This is taking the charges from the cloth and it is passing them through the meter, and to complete the measuring circuit, charges are coming back out and into this read of the meter. The reason why they come through is because the tendency is for charges to pass through a conductor from a higher potential to a lower potential. If I break the measuring circuit, the meter reduces to 0 eventually. To check that the meter is working correctly, we short circuit these two, and that is 0 on the meter. There is no difference in the potential of the red probe to the black probe. Now put them back into the electrolyte, and we see that there are 5.2 volts difference between the electrolyte here and the electrolyte there. Now, this is the anode of a corrosion system. The charges are coming from these corrosion cells, which are batteries, and the charges are coming through the black lead and into this nail here. They are passing through the electrolyte to this nail here, which is attached to the negative lead of the batteries. So this is the corrosion cell which we have deliberately made to show that the charges are passing from the positive through the electrolyte into the negative. The positive is the anode and the negative is the cathode. The cathode is the equivalent to the pipe. The pipe is cathodically protected from corrosion because the charges are coming from the electrolyte into the pipe. If we turn these, then we have merely affected the meter. A negative sign has come on the meter and the value is very similar. The value on the meter is totally dependent on the position of the probes. If I move this probe closer to the anode, it will be a higher reading. One closer to the cathode, it will be a higher reading. As I bring the probes closer together, the reading will get lower because the difference between the charges in the electrolyte at the positions that I have the probe are different potentials in the electrolyte, and this is shown on the meter. If I leave this probe in the same position and move the other probe, the value in volts will decrease. This is now 0.73 volts. It's now 2.86 volts. Now 3.8 volts. It's now 5.4 volts. Now if I put this probe on the actual anode, this probe on the actual pipe, then we get the full value of the voltage of the source, which in this case is 6.242. So it is the position of the probes in the electrolyte which is charged up to a greater or lesser degree. It doesn't matter if we put a copper sulfate cell on here. If we put this in contact with one probe, it will not stabilize. You will notice the position of the copper sulfate is merely to the position of the probe. So with the copper sulfate in this position, it shows we have 4.2. If we connect this to the pipeline, it shows we have 6.024. But if we put copper sulfate here, it shows 0.65. Pick that up, yes. 1.2. 0.76. It is not protected. It is not protected. It is protected. It is overprotected. So this demonstration shows that the copper sulfate electrode is not a standard reference potential for pipe to soil readings. Come off, let's get back onto there. So we can see that by measuring the potential of the ground in which a pipeline is placed, buried, imagine that this is the anode of a cathodic protection system, and this is the cathode of a cathodic protection system. We are protecting the cathode, which is the pipe. If we just consider that this is a corrosion cell, it's the same. This is the anode, which corrodes. This is the pipe, and this is the cathode of the corrosion cell, which doesn't corrode. And we can measure this in volts. So we effectively, using this demonstration, we can measure the voltage on a closed circuit corrosion cell, because all of this is contained in one place. Now, when we come to the center nail, the charges are higher here than they are here. So we have the cloth charged here at 0.566 with respect to the cloth there. This means that there are about 0.6 of a volt potential difference between this cloth, which is high, and this cloth, which is low. So the charges are going into this nail here and out of the nail here. Now, where charges leave the electrolyte, the metal, sorry, they carry with it metal which is dissolved. That is what Faraday said. Faraday was right. So we would expect now, according to Faraday, to see the metal of the nail here is protected, it's not corroded, and the metal here to be corroded. And we can actually tell the potential of the metal in relation to the electrolyte. So we are getting a discharge in this area, and we can measure the discharge on this 3 nails demonstration. Now the reason it's 3 nails, we've got 2 nails, is because the centre nail represents a foreign pipeline. And what we are seeing here is interference or stray current. The current coming from here passes onto this nail or pipeline at a coating fault, which becomes cathodic, and off of the foreign pipeline at this point, which is anodic. So if this were our pipeline, this would be protected by the foreign cathodic protection system. This would suffer accelerated corrosion, which would be interference or stray current corrosion. And we can actually measure this. Not only can we measure all of these effects, but using the 3 nail demonstration and just going purely visual. This was set up yesterday, right? And in 24 hours or less, we can actually see the corrosion products. This has corroded, and there are corrosion products to be seen on the cloth. You can also see that the nail is corroded. You can see the corrosion products on the nail. This is not corroded at this end, and you can see that it is bright at that end, but corroded at the other end. So you can actually see the corrosion. This is the protected nail, or the pipe, and you can see no corrosion at all. You can see no corrosion product there or there. You can see a certain amount of corrosion here due to the difference between this nickel-plated crocodile clip and the steel, and that has caused a tiny bit of corrosion at that point. So here we have a perfect demonstration of corrosion itself, how it happens, and the results of that corrosion itself.